Hi, everyone in the room and those watching who couldn't get in, sorry. Yeah, there's been a lot of talk about LLMs and generative AI, and one of the main innovations here was almost shockingly simple, like just make the models bigger, like a lot bigger. And with all of these new models coming out, bigger and bigger behind APIs, run by big tech, I think it's fair to wonder, are we going further and further into a black box era with larger models obscured behind APIs, monopolized by big tech? And as you can tell from the title of my talk, I don't think so. I actually believe that open source means there's no monopoly to be gained in AI. And it's also what led me to found an open source company. So some of you might know us from Spacey, which is an open source library for NLP. Spacey was really designed from day one to be used in real world applications. And we've always put a lot of work into like all that boring stuff like backwards compatibility and stable APIs. And this had a really nice side effect more recently because ChatGPT is actually pretty good at writing Spacey code, at least for now, until it's like polluted by all the auto-generated content on the internet. And we also developed Prodigy, which is a modern annotation tool for data development, and it's fully scriptable in Python. And that all led to our current new product that's currently in beta, which brings Spacey and Prodigy into the cloud and offers a collaborative data development platform without compromising on data privacy and scriptability. And a lot of the ideas that I'm talking about in this talk today actually really directly inspired the workflows and the philosophy of this tool. So open source, if you if you're here, you've probably used open source software before. I always like to do a show of hands, like who's contributed to open source software before? Oh, wow, that's good. And who works for a company that relies on open source software? Wow. Yeah, that's a lot. So, there are plenty of reasons why companies choose open source. And one of them is it's transparent. You're not locked into any provider. It's very extensible. You can, script with it. It runs entirely in-house. Nothing, needs to leave your service. It's easy to get started. Just pip install, run a library, run a new tool. It's also community vetted, so you can see what's popular, what other people are using, and it's also programmable. So, you can work around it. You can fork it if needed, and many libraries and tools are also very up-to-date because they're developed by small teams. They can accept community contributions. And if you're looking at this, you might notice that one of the aspects that people very commonly associate with open source hasn't even made this list, which is that it's usually free. And I think it's the reason that open source software is free is not really why companies use it. I think it's a nice add-on that really helps with some of the other things like community vetting and getting started. But I don't think companies use open source because it's free. They use it for all the other reasons here. And since we're talking about AI and machine learning today, of course, there's more than just software. We're talking about code plus data. And there's been a growing ecosystem of open source models that are published and that you can use. And those roughly fall into three categories. So on the one hand, we have what I'm calling task-specific models. That's things like the models we distribute for Spacey, community projects like SciSpacey for biomedical text. Stanza from Stanford also published their models. There's a lot on the Hugging Face Hub. So these models are small. They're pretty, fast, especially, for today's standards. They're cheap to run, but of course they always don't always generalize well because they're trained for a specific task and they need data if you want to fine-tune. And then we have another category that I'm calling encoder models, which includes Google's BERT and local variants like Alberto for Italian. And these models often also power the task-specific models and are used for encoding. They're still relatively small and fast. They're affordable to run. They generalize and adapt pretty well. And they also need some data to fine-tune them if you want to make them do a specific task. And then finally, all of this development on these encoder models has led to a third category, which is the large generative models. And as the name implies, they're very large, they're often slower and expensive to run, but on the other hand, they generalize quite well, and they need little to no data to make them do a very specific thing. And one thing that doesn't really help here if you're looking at this is that pretty much all of these models have been called an LLM at some point or another. And I think that really confuses the discourse and actually leads to a lot of confusing ideas that people have about the question of, who's going to control these models. And I think there's actually a very important difference if you're looking at using these models to do a specific thing. So if we're comparing the encoder models and large generative models, in the encoder models, you're actually training a task network and you use the model to encode the inputs. And in comparison, if you're using a large generative model, there's no task network. You're basically using a prompt template, usually combined with a parser that takes the human-readable output and converts that into structured data, and it generates text. So I think this is an important difference, and it also really informs the ways we use these models and the workflows. I'll try to avoid the term LLM going forward to not further add to the confusion. And task-specific models and encoder models have been pretty established, have been running in production for years at this point, and many companies are also exploring large generative models and are adopting them. But since these models are very large and can be expensive to run, there have been a lot of providers that offer access to these models via an API that you can pay for. And how is this possible? How can companies offer these models for cheaper if they're open source and freely available? And the simple answer to this is, well, economies of scale. So companies like OpenAI and Google, they're very large, so they're able to hire the best people, they have access to compute at wholesale prices, and they can basically offer access to these models cheaper than companies that are much smaller. And there are all kinds of other business reasons why larger output leads to lower costs. But in the context of AI, one thing that's important is that GPUs are incredibly parallel. So you can batch up the requests, and of course that means you either have to wait for enough texts to be available, or you have to have a really high throughput that if your tool is very popular, you can batch up a lot, and you can't just arbitrarily chunk up the text. So you need to have enough traffic. So you can think of it a bit like a train schedule. So in a large city, you can have a train running every 5 minutes. In a small town, that's not possible. So you might have a train only once every hour, and it simply waits until there are enough people to transport. And that's the same idea here. So what we can see here, though, is that we're basically having companies compete on price for these models. And that's kind of the opposite of a monopoly, really. That's competition. But still, the question is, well, how are you going to keep up here? Are you doomed? Not quite. So another distinction we have to make here that I think also really kind of muddies this discussion is the distinction between human-facing systems and the machine-facing models. So on the one hand, we have products like ChatGPT, Google's Gemini, and then we have the models that actually power these systems. So that can be GPT-4 or Bard. And for humans-facing systems, the most important differentiation really is product, not the technology. So, you have the UI, UX, how nice is the product to use, how is it marketed and presented, and also everything around it. We don't fully know how ChatGPT actually works under the hood, but there's probably a lot implemented to prevent the model, for example, from outputting offensive content. And that's all, around features implemented around the model and that make a product. And on the other hand, the machine-facing models, they're really swappable components, and they're based on openly published, openly available research, and their impacts are quantifiable. So that includes speed, accuracy, latency, cost. And that's really, these models are publicly available, and they're powering these human-facing systems. So there's a clear difference here, and AI products, they're not just the model, and also, models are not equal to AI products. So you might be asking, well, but what about the data? Like, don't OpenAI or Google have enormous amounts of user data that they can use to build better AI? And that's definitely true, but user data really is an advantage for product, not the foundation for the machine-facing tasks. Because if we've learned one thing from all the recent developments, especially in generative AI, large language models, whatever we mean by that, we see that you don't need specific data to gain general knowledge. That's really, that's what this is all about. So OpenAI might very well dominate the market of AI-powered chat assistants, but that doesn't mean that they'll also monopolize or dominate AI. So the machine-facing models, that's really what we want to be talking about when we're talking about AI and LLMs. And if we're looking at what people are actually doing with these things in industry, there are basically two types of tasks. One is generative tasks. So that includes stuff like summarization, question answering, style transfer. And these are things that really have only become possible with, to do reliably and to actually do well with a lot of these larger models. And here you have, text going in, and what comes out is human-facing output. In the form of an answer, for example. And then on the other hand, we have predictive tasks, where text comes in and some kind of structured data comes out. So that's text classification, entity recognition, things like grammar, relation extraction, and so on. And while there are a lot of new capabilities that have been unlocked, if we're thinking about one of the fundamental problems, or why we're all here today, is that we really, the main thing we're trying to solve is bringing structure to unstructured information. And a lot of these industry problems actually haven't changed very much, even since before the introduction of computers. Like, if you're working with index cards, yes, there's just a limit of how much you can do and how much you can, structure your data. And then with computers, you have basically more options, and you can do more projects. So while there are new capabilities and new things you can also do a lot more of the thing you've been trying to do since even before we had computers, which is produce more structured data. And now, if we're looking at how are we telling computers what to do? Well, in the beginning, we had the option of defining rules or instructions. So that's like conditional logic, regex, other rule-based systems. And then with machine learning, that unlocked another way, which is programming by example, also called supervised learning. And then finally, with in-context learning and the new models, we unlocked another way, which is defining rules and instructions in a human format, so prompts. And there are kind of pros and cons here if we're comparing those different workflows. So instructions are really inherently human-shaped. They map how you would tell a human what to do, and that makes them very easy to adapt for non-experts. You can just write what you want the system to do. But there's also a risk of data drift. So if your model changes, if your data changes, those rules and instructions might not apply anymore. And then for examples, well, those let you really express very nuanced and intuitive behaviors, like things where you know what the answer is, but you can't necessarily articulate why. You just know that it's true. And it's also very highly specific to use cases. So you can provide examples that are really specific to the task you're trying to solve. But one of the biggest problems has always been that this is very labor intensive, and you need to do a lot of it, and you need to do it in a consistent way. So the question is, well, is there a way we can kind of combine the best of both worlds and come up with a workflow that is actually better than just the individual steps separately? And To give you an example here of how this could look, on the one hand, we have a large general purpose model that can do a lot of things and has like a lot of weights. And then we have domain-specific data that's really the stuff you're working with and that you want to answer questions about or structure in some way. And what we can do is, well, we can, of course, prompt the large general purpose model. And we can also benchmark that. So that's a very important step. Like, we want to know how well the system is doing out of the box. So we get a baseline that we can record, and that's kind of also what we want to beat here. And then we can basically pipe those examples and the results of the structured data that comes out of the prompt into an iterative process where we can look at the examples, we can correct them because there'll always be some mistakes, and then we can save and extract the data that's only specific to the thing that we're trying to do. And then finally, using transfer learning, we can train a distilled task-specific model that really only contains what we're looking for, and we can evaluate that and basically do it until we can beat the baseline that we've determined earlier. And transfer learning is really a powerful tool here. And just because we now have in-context learning available doesn't mean that transfer learning is somehow outdated or has been replaced. It's simply a different technique that we could use for a different purpose. And here's an example of how this can look if we're prototyping versus productionizing. So here we have a pipeline of components. During the prototype phase, you can use a mechanism to basically prompt the model and turn the output into the structured data. So we thought about this a lot. We've built this for Spacey LLM, which is an add-on that lets you swap in all kinds of different models, from APIs to open source models. So you basically have the same output that you also want at runtime. And then you can swap, mix, and replace those components for your production process. So you can distill all the specific behaviors that you want, and in production, you basically have a pipeline that runs entirely in-house with very small and fast components that have the same behavior than what you had when you prompted the model. Now, if you look, what are the advantages here? So, of course, this approach is very modular. You're not locked in. You control your pipeline. It's very testable. You can test the components individually. It's extensible. Can program around it. It's very flexible. It's cheap to run. Like we've seen, people build models that are under 10 megabytes or even 400 megabytes. That's like a very different story. That you can really control those models that you've developed. It runs entirely in-house. No data needs to leave your servers. And it's also programmable. Very rarely the machine learning or extracting structured data is the sole purpose. You usually want to feed that into another process, and you can easily do that here. It's predictable. You can you know what your model is supposed to do. It only does a specific thing. You don't have to worry about your model going rogue, and it's very transparent. You can really explain what it does. And often also why. And if we're looking at all of these advantages here, we'll notice that this is actually very, very similar to what we've identified previously as reasons why companies are using open source. And that's not a coincidence. Ultimately, AI development is really just another type of software development. And so it makes a lot of sense that we want the same software engineering best practices in the software and open source tools that we use, but also in the types of models that we build. And now, there's been a lot of talk on the Zen of Python. It's come up in plenty of talks, which is why I added this slide back. So, this line in particular, I think it's easy to forget that, like, hey, these are, there are principles that have made software successful, and we shouldn't just abandon all of that and everything that we've learned because, like, hey, there's a new paradigm, baby. Let's throw all of that away. So, to come back to the initial question of monopolies, they're basically, they are, if you want to, if you have a company and you want a monopoly and get rid of all of this pesky competition that companies and investors hate so much, there are different strategies, and companies have been, very actively pursuing them. So on the one hand, we have, a compounding advantage. So that can include network effects, which is like very common for social apps, or also economies of scale. But what we've seen earlier is that economies of scale alone is actually a pretty lame mode. And if you're not if you don't even need to rely on these models in production, that really changes the game a lot and means that you can even potentially run things in-house. This is not necessarily what's going to give anyone a monopoly here. Then the next idea is, well, controlling a resource. That's not really a thing here. We don't have an AI mine or something like that, so that doesn't apply. And then finally, the third point is, well, regulation. That's very attractive because, hey, if basically you have a monopoly because the government says so, and that's if you can get that, that's of course very awesome. But what we have to really consider here is this distinction between the human-facing products and the machine-facing models. It makes a lot of sense to regulate products and actions, but what we don't want to do is regulate the machine-facing models that are based on research and that are essentially software components. And because if we're not careful here, we might actually end up gifting someone a monopoly for all the wrong reasons if we're not being careful and making that distinction. So now, to sum up why I think there's no monopoly in AI, one thing that we've seen is there really no deep internal secrets here. Like, the software industry does not run on secrets, and research will always get shared and published and will be available. So there are no inherent AI technological secrets that will give anyone a monopoly. Also, user data and data that big tech companies collect is very valuable, but it's valuable for products and product experiences. It doesn't generalize, and it won't give anyone a monopoly or a lead on AI simply because they have user data. It can only give them a lead in a product category. And also, if we're looking at LLMs and large generative models, they're usually a software component. They can be part of a product, and they can be swapped for different approaches and different components. You can use them at development time and swap them for distilled components at runtime. And this kind of interoperability is really what's powered by open source, and it's what open source is about. And that really is the opposite of a monopoly. And finally, yes, regulation is something we should be careful about, because this is really a way that someone can gain a monopoly. And regulation should focus on products and use cases and things people do, not software components. And because if we have big tech leaders lobbying in front of Congress, warning about the dangers of AI and basically advocating for regulating software components instead of products, their intentions might not be exactly pure. So, thank you. Yeah, I made it in time.
Thank you very much. Very interesting topic. I forgot to remind everyone before that you can submit your question online. If you go on this room, in the schedule, you can submit a question. I will read it out for you. But we have already 2 questions.
Yep.
So first one, big players like OpenAI are planning engine to recognize their own AI-generated content for avoiding misuses. Do many open source Gen AI pose a risk, for example, for spreading disinformation?
So what's the question? Like, if having models available is a risk?
Yeah. And also maybe that these open source don't have their own way to recognize if they generate the AI content.
Okay, but I think if you're talking about models in general, I mean, the cat is kind of out of the bag. So it might, yes, there are risks, but it might as well be open source and openly available. And I think there's also a lot of research going on about detecting AI-generated content. And that's also something that comes out of the research that's openly published and then implemented by companies. And I think there are definitely also open source models that can, do that. And ultimately, it's really about like what you do with the model. Like the problem is, spreading misinformation. The problem is, using it to in bots on social media. The problem is not the model itself, which basically just generates text. So I think that's the important distinction here, basically.
Cool, thank you. Next question: do you think that this specific tasks model could be attracted also for personal use, or are we talking mainly about business use cases?
Personal, I mean, it's definitely something you can also, do. There's actually, what I find very interesting is there is a lot of work done on, maybe having on-device models in products and in tools that you use, like, a browser or other things that basically, have your data. So I think there is like a lot of opportunity to basically allow users to train their own components that they can own and have have on their machine. And I think that is definitely for personal use pretty cool. Like imagine, instead of sending everything to an API, you could run these small models locally, and that is definitely possible with this approach.
Sounds good. Next one, using small generative language model running locally, for example, with Ollama, may also be an alternative for generative use case. What's your take on this?
Yeah, definitely. I mean, there's a lot of smaller models coming out that are, fine for a lot of use cases, because usually use cases are specific, and you don't necessarily need to transform everything you want to do into arbitrary language and find the biggest arbitrary model. Running small models locally is fine, definitely good approach. Also, again, if you're primarily using them at development time, then it's also totally feasible to run them yourself, and it's not going to be as expensive as it would be if that's like your main component in production. So yeah, I think all of these developments are very exciting.
Next one is, what's the best AI? Okay, that's
the best AI.
I don't know, that disappeared. Okay, I have another one. What about training data? Should be publicly accessible, like models as GPT or similar?
I mean, a lot of there is a lot of the data, like the pile and all of the internet data that people are using to train these models is kind of available, and there are a lot of questions around, copyright and scraping the internet for the data. And then I think on the other hand, there's like the data you create for a specific task, and I think often that is something companies can keep internal, and often, sure, that makes sense. That's like, your specific data, and basically with an approach using transfer learning, you actually don't need very much to define specific behavior that you need, and you can really, you can control your data in-house and then use, and for the generative component, use something that's publicly available, open source, trained on data that you kind of know.
And I think I have the question that disappeared before. So what's the best AI strategies to retrieve insights from structured data, like contracts, patient data, etc.? Fine-tuning, SQL agents, distillation, RAG?
I mean, it depends on, what you're doing. Like, I do think if you're working with, something like contracts, a lot of this data is stuff that, you don't necessarily want to send to third-party APIs, and that makes things pretty difficult. But, you can start out prototyping with a large generative model, and then really, you really identify the parts and the categories and the types of structure that you want, and approach each of these components separately. Like, even for something like text classification. There are a lot of systems that are like, what, 15, 20 years old that can absolutely outperform any large model that's out there. And you can, choose that for one component. And then for another component, you might, want to generate text or summarize your contract or summarize your document. And then you use, smallish large language model for that. And then after that, you might combine it with some regular expressions and then have another component where you train an encoder model. So I think that kind of flexibility, I think, makes sense. But of course, that also means, you need good tooling that really helps you iterate and reason about these things. It is not an end-to-end process. And I think, but that also makes sense because I think like reality is also not like an end-to-end prediction problem. And, there's always going to be work. Like if you have a real-world process and if you have a real-world problem, there's always going to be, you have to reason about what you're doing. And AI is not going to magically absolve us from that.
I agree. Unfortunately, we don't have any more time. I saw other questions. Will you be around to answer?
Yeah, of course. I'll be here today, tomorrow. And I have stickers. Including a new one with, my talk title. So, come up. Like, if you take stickers from me, because the more you take, the less I have to carry back to Berlin.
Thank you.
Thank you.
Thank you.